Okay, so where we left off last time was with this question. How are these curves constructed? Did we wait 100 years and follow every single person to death and then construct the curves like we did with the 10 sticks? And the answer is, of course not. We didn't do that. How these are constructed, we have to go back to Halley, Edmund Halley. He of Comet fame. He actually wrote 2 papers in statistical methods, probability, whatever you want to call it, and at the end of the 17th century. And what it was he was approached to tackle this problem of how to construct these curves. And it just so happened that the reason why he was approached is that somebody by the name of Caspar Neumann had been collecting some fascinating data. Now, Neumann was way ahead of his time. And what he had done was he had collected 5 years of mortality data from the town of Breslau, which is where he lived, which I think at that time was part of Germany. Now it's part of Poland. And he had 5 years worth of mortality data. And what he was interested in, which was, as I said, way ahead of his time, first of all, in collecting data on people, and secondly, in testing the hypothesis. He was a minister, and he was very much interested in astrology. And there's some theory in astrology that you're born when the moon is, or the planets are in a certain house, and you're going to die when they're in this, I don't know, something like this. He wanted to test this astrological, I have no idea what it means, but he wanted to test this astrological hypothesis. He tested it, and he showed that astrology was nonsense. Fine, but now he had this fabulous data, 5 years worth of data from Breslau having to do with mortality in Breslau. So they presented this data, the Royal Society, to Halley. And what Halley did was he constructed the very first life table using the methods that we still to this day use. And here is Halley's life table of Breslau at the end of the 17th century. And you can see that initial mortality, if one is to trust these data, that initial mortality is extremely high. That by age 10 or so, look what happens by age 10. What is that about? There's only about 60% reach age 10, maybe a little bit more than that. So it's a fantastically big precipitous drop here. And then after that, look at this, it's very interesting. It's almost like a straight line. That's the life table. Now, in numbers, here it is. And with the numbers, it's easier to explain to you what he did. So he said, suppose we started off with 1,000 people. So here is how you read these data. So you start off with 1,000 people in their first year of life. How many will reach into their second year of life? And that, the number he calculated was 855. And then how many reach their third year of life? Of those 855, 798. And of those, 760 will reach the fourth year of life, and so on. And we read up and down these columns. Then there's the 8th and 9th, and then there's the 15th year of life, the 22nd year of life, 29th, etc. And he took it down to 84. Okay? And of the original 1,000 people who were born, 20 reached the age into their 84th year. Now, where did the ingeniousness? Now, he published this in the Philosophical Transactions, and it's funny because, well, I thought it was a little funny, because if you read the cover of the thing, it says, this is a philosophical transaction, and what it is the accounting of the ingenious. So they used to report on people who were ingenious. So in this case, it fit him very well, of course, but it's a little presumptuous. Not even the New England Journal says that. But so getting back to this, what he noticed and what was really ingenious about this is how did he go from 1,000 to 855. What he did was he said, what percentage of those 1,000 die? That's how we get the 855. What percentage of kids die in the first year of life? And then let's look at what percentage die in the second year of life, and what percentage die in the third year of life, and what percentage die in the fourth year of life. What he then figured was, I don't need those numbers from this particular cohort. I can get the percentage who die in any 1 year from any cohort. A meaningful cohort, of course, but from any cohort. And then I can put them together in a meaningful sort of way, and that's how I'm going to construct the life table. And that's exactly what he did. That's exactly what he did. So, for example, if we go back to these tables, just look at this curve, just look at the 2006 curve, and ask what happens between the ages of 65 and 70. So what happens here? These are the people who have survived to age 65. Suppose we know that point. Then how do we get this point here? Well, if you just tell me what percentage of 65-year-olds will die by the time before they reach 70, that will give me this point. Okay, so if I know this point, if I know that point, and I know the percent who die in the next 5 years, that will give me this point. And then I can repeat that logic to get this point, and then this point, and then this point, and so on. And like that, I can build up the whole curve. That is what he did. That's what Halley did. Let's look at it a little bit more specifically. He says, we don't know what will happen to the 65-year-olds in 2072 because we're not there yet. So we can't follow this cohort till 2072. But we do know what happened to 65-year-olds in 2007. We'll just follow them up for a year, and we'll see how many die in the next year. Follow them up for 2 years, how many die in the next 2 years, and so on. And then I can tell you what happened to 65-year-olds in 2007. I can also tell you what happened to 66-year-olds in 2007. I can also tell you what 67-year-olds in 2007. If I can project that age-specific mortality into the future, in other words, if I can say, all right, if this remains constant in the future, then I'll use that. And I'll get a realistic construct that way. And that's exactly what he did. And that's exactly what he did. The life table methodology constructs a life experience for a cohort. It's a fictional cohort, but it's a cohort subjected to current mortality rates as that cohort progresses through life, as if the current rates don't change. Let's look at it a little bit more closely. In 2007, let's take a look at what happened in the first 20 years of life. That's because I can only put 20 years of life on this slide. Let's see what happens. If in 2007, I look at all the babies born in 2007 and I follow them up for 1 year. So that means baby born on January 1st, 2007, I have to follow up until January 1st, 2008. Baby born on January 2nd, 2008. So every baby is followed for a year. That means I have to observe everything for 2 years. Because for the babies born on December 31st, I have to follow them up for 2 years. So I'll have my data. Within 2 years, I'll have my data. Look at all those babies born in 2007 and see what proportion of those babies pass away in the first year of life. Okay? And that is this number here. Now, they've stated it as probability. Forget about probability for the moment, because we'll come to that shortly. And let's just call it proportion. If you call this proportion, we'll see later that proportions and probability are roughly the same thing. So the proportion dying in the first year of life is 0.006761. And that we get from the people born in 2007. Right? Now, what about kids in their second year of life? In 2007. What proportion of them died within a year? And the answer is this, is 0.000460. So once again, I need only follow them up for 2 years. So for the ones who turned 1 on January 1, 2007, I have to follow up for a year to 2008, all the way down to December. I have to follow for a year to that. Okay, so within 2 years, I get both of these points. And the same is true for those between the ages of 2 and 3. So those in their 3rd year of life, I find by following them up for 2 years that I get this number, which is 0.000286. So that's the proportion who die. So in fact, this whole column here, this whole first column here, all these numbers, and all the way down to 100 or whatever the lower number is based on observing this cohort over this very, very short amount of time. Okay, so these are the age-specific mortality rates for the 2007 year. Not the 2007 cohort, but the 2007 year. Now, to actually ask that other question, which is, all right, so after 2 years, I know what happened to babies in their 1st year of life. What about the babies born in 2007 in their 2nd year of life? Now I have to move into 2008, 2009 to get that. Okay, in the 3rd year of life, I have to move into 2009, 2010, and so on if I'm going to follow this cohort through life. And I can't, very quickly I'll run out of time because we're in 2012. All right? But what I can do is I can apply these numbers I've got here to that cohort. So let me construct a fictional cohort and subject it to the current mortality rates. So let me start with 100,000. Apply this proportion dying. So of those 100,000, we're saying 0.006761 are going to die. So that gives me 676. So 676 are going to die in their 1st year of life. What does that leave me with? Well, 100,000 minus 676, which is 99,324. Let me look at this proportion of those that are going to die. So the 0.000460 times this will tell me how many of those kids will die in the following year, and that gives me 46. Subtract 46 from 99,324 gives me 99,278. How many of those are going to die in the subsequent year? I multiply by 0.000286 and I get that 28. And subtract that from 278 and I get 99,250, and so on. And I keep on doing this, boom, 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 boom. So I'm creating a fictional cohort and applying today's age-specific mortalities to that. And what do I end up with here and carrying on down is my survival curve for this cohort of 100,000 people. So remember, our survival curves start off at 1. So to get that, I just divide by 100,000 people. They do this, they introduce the 100,000 just to make the arithmetic look simpler. But just once you're done, just divide by 100,000. And then that's our survival curve. The question then is, how good is this survival curve? Well, we go back to these age-specific mortality rates we've already seen, and we see that they are pretty constant. Most of them are going down. If there is a trend, there's the trend going down. Except remember we noticed this, the Second World War, but other than that, the trends tend to go down. So the trends going down mean that our method of doing the life tables is conservative. If these trends persist, because we've only noticed these trends up until today. What is going to happen in the future, we don't know. But judging from the last, what do we got here, 60 years, then if what happened in the last 60 years continues to happen in the next 100 years, then what we're doing is estimating it rather conservatively. But there isn't, except for some age groups like the under 1 year, where the under 1 year, here's this for women, is very the trend is steep. The very young ones, the trend is very steep. The 1 to 4 and the 5 to 14. By the time you get to the 15 to 24, already things have flattened out. So for the early ones, it's very conservative, but for the latter ones, latter ages, the older ages, it seems like it is a little conservative, but we don't really know because we don't know what these rates are going to look like 10, 20, 30, 40, 50, 60 years from now. Nobody knows the future. Okay, so what we do is we estimate using this constant mortality, that today's mortality numbers will hold into the future. Now Halley, I should add that Halley made one extra assumption. You see, when we calculated this proportion dying, to get that number we have to know how many kids are in the population, how many were born, how many died. He didn't know that. He didn't know how many were in the population in Breslau. They didn't have a census. So he made this extra assumption, which was this stable population assumption, which basically says the number of kids born is equal to the number of kids dying within any 1 year. And he said it's a little bit off because of that, but other than that, it doesn't matter. What we got out of this was a method for doing the calculations. And as I said, it's proved invaluable in that we still use it more than 300 years later. So there's his table, and it's been a fantastically important development that we still, 300 years later, gathering the benefits from this construct.